This is Smarter Cars, a podcast about autonomous vehicles.
This is the finish line. The Stanford racing team has made its way into the history books.
But the most important thing for me is it actually doesn't matter who comes first. It matters that we as a community achieve it.
Early in a technology, a thousand flowers should bloom.
Welcome back to Season 2 of Smarter Cars. This is your host, Michelle Kairouz. Today we're talking with Blair LaCorte, president of Aeye, a company making next-generation Lidar and perception systems. Blair, welcome to the show.
Hey, well, thank you for having me.
Absolutely. For those who don't know, can you tell us what Aeye does and what your mission is?
Sure. Well, first of all, we have the coolest name because when you say it, you think of the real message that we have, which is that, that we're actually going to think smarter and better and actually add value. But Aeye started really as a company that was tasked with trying to figure out a way to actually take some of the lessons we've learned over the last 20 years in visualization and the Army, intelligence, and aerospace, and actually translate them into the commercial markets. So we really started with a different problem than most companies have, which our job was to figure out how to enable perception, not how to build sensors. And most of the people that have founded the company and have been hired in the company are people who have built vision systems, everything from ISR systems to automated targeting systems to security and sensing systems. So they tended not to just be about one sensor. Although we have invented a very unique type of Lidar, we invented the type of Lidar because we needed it to complement the other things in our system, not because we believed that Lidar was the only sensing system.
Right. So tell us what Aeye is making in terms of this product that you're referencing.
Sure. So the initial challenge on the whiteboard was, how do we, again, transition a lot of the technology from the last 20 years we had been developing in intelligence and aerospace and defense and create a system that could see better than a human, right? How could we perceive better than a human? Not how one piece of it could see better, but how the system itself could see better. So we actually looked at all the sensing systems that we could find over the years, and we built an architecture that allowed us to replicate or biomimic what a human visual cortex would do. And there were four key things that we looked at the beginning. One was that humans today see a lot better than autonomous cars. And the reason why is we not only scan spatially, but we also change our temporal interrogation of the environment. So when we foveate and see something interesting, we may focus on that and update faster on those objects than we're updating other objects in the scene. So the first thing we needed to do was to build a sensing system that could spatially interrogate an environment, but also change the temporal interrogation. The second thing that was a challenge for us was the human eye actually can see in 2D and 3D. Now, the human eye abstracts it using mathematical formulas, and there's a distance limitation to it. But one of the things we decided was that there is a system out there called Lidar that when you combine with 2D systems actually give you that capability to modulate both in 2D and 3D at any point in the scene. The third thing that we decided was that if you look at how humans visualize, 70% of visualization is done in the visual cortex at the edge of the brain, not in the core center of the brain. And that 40% of what we process in our visual cortex is actually highly impacted by what we'll call trigger senses. If I hear a sound, I foveate left. If I have a smell, I relate that smell to fire, and I look for red, so that we take shortcuts to interrogating a scene. And the final piece was that the human brain is all software definable. So while we have pieces of hardware like our eyes and our pupils and our visual cortex, we change that by how we actually get feedback and how we change the inputs into say, what do we want to look for and how do we look for it, right? So those are the four reasons that we created what we'll call a system called IDAR. Now, it is, kind of cute, just like our name, that we didn't want to be called a Lidar. We said IDAR is intelligent detection and ranging, but there was really a fundamental reason we did that was to stop people from necessarily thinking about things as a point problem and starting to think of things as a system problem. So our IDAR system actually addresses the four things that we talked about. It allows you to intelligently scan a scene versus unintelligently scan a scene. And it is definitely built on giants. I mean, 15 years ago, there was a lot, DARPA challenge, and a lot of people came out with Lidar. There's been a tremendous amount of advancements in computer vision over the years. There's a lot of technology for in GPUs for distributed, analysis of data. So while we're using some of the things from the industry, the way we're architecting it is what actually makes us different. In essence, IDAR is an architecture that can take any new innovation and combine it into what we believe is a better way to visualize the world.
Interesting. Well, super interesting that you started from, the human visual cortex and thought about kind of reverse engineering that backwards as to what the component parts would be. And so let's talk a little bit further about IDAR and sort of how you put it together. So you take a solid state LiDAR, and then how does that work together with the HD camera and other pieces of it?
Right. So, again, as you said, if you look at a problem differently, you're going to come up with a different solution. I would say that 7, 8, 9 years ago, and it has been accelerated recently, as people were just thinking, listen, computers are better than humans. Computers are faster than humans. They don't get distracted, and 94% of accidents have something to do with human distraction. So I think the pendulum swung so far over to that computers are better at visualization than humans that we just have to figure out what a computer does well, and we'll take that and we'll apply power and time to it, and it will give us the answer. Our assumption is still that if you look today in autonomous vehicles, which we've spent a tremendous amount of money and we have some great people working on it, the average autonomous car functions at about 10 hertz, and it is geofenced and usually in very discrete sections where we have HD maps. And when you take a look at it's the way it interrogates the environment, it uses the same density everywhere in the scene, and it brings it back to the center. So today, a human can see much, much better than an autonomous vehicle. I mean, humans can scan the scene at 27 hertz for complex objects, and if they know what they're looking for, it can go to 60 or 70 hertz. Humans can foveate so that they don't put the same amount of effort into the sky behind me as the girl in front of me that's ran across the street. Those are things that's why today when you see autonomous cars out there, and by the way, there's been great progress, they're still not the equivalent of a human paying attention. So what we have done is actually taken those components and said, let's go one by one down the stream. If you're going to put something on a car, it should be solid state. Were the systems originally designed that spun around? Absolutely. And that was the right way to think about it back then, because they were trying to figure out how to get 360 degrees. And at that point in time, that's the way they figured they could get 360 degrees most effectively. So they did spinning systems. Now, the downside was that they were actually, mechanical systems. One of the other things that they did 15 years ago that as incremental would be based in silicon, so that it'd be very inexpensive, thinking I've got to make these systems inexpensive over time. Those two decisions that were made 15 years ago have actually impacted more than anything else the ability of 3D to be melded into a vision system, because all of the original LiDAR systems were spinning systems, and therefore mechanical, and they were focused around silicon, and therefore they were focused on a very specific wavelength we'll call near IR or 900 wavelength. The second generation of systems, to your point, once you've played with the systems and once you put them on cars and you started to pilot them, you realize two things are probably fairly clear. One is that you have to have a solid state system. Now, solid state, is in some ways relative in that the physics of solid state would be nothing moves, whereas the implication of what a solid state system is that it can't be impacted by 9Gs of shock, that it can have temperatures that range, very low and very high, that it can be easily produced, it can be scaled. So we look more at what we would call the implications of solid state. So in essence, our system, while it does use MEMS mirrors, which is one way you get to Lidar, they're a very unique design, and they replicate what solid state is. In fact, in the military, we would have used them in 500G Gatling guns and in very high temperature laser resonators. So for years, we know how to replicate solid state. So I think that every 1, 2, or 3 years from now that has a vision system, if they have a 3D component using Lidar, it will probably be solid state, and they'll probably be moving off some of the wavelengths like 900 and probably to more malleable wavelengths that have longer arcs and that can be modulated and amplified. So those are the two basic concepts that we assume would happen in the second generation. And so for those of you out there who are going to look at Lidar systems as part of a bigger system, you'll find that almost everybody today talks about solid state, and they talk about different wavelengths than they did before with just 905.
Right. So when you were thinking about human vision being both 2D and 3D, you decided to take the 3D with this solid state LiDAR and then try to put it together with 2D by fusing that with camera data?
Right. And again, if you look at history, there's the idea of having camera 2D data and LiDAR 3D data has been around for a long period of time. The challenge with it has been that when you take two different sensors, you have to fuse those two sensors together. And there's a whole process that's very well known called 4D fusion. And so, 4D fusion means that I'm not collecting data simultaneously, but I'm fusing the data after the fact. That, again, works in pilots, but after you start to realize that latency matters, that time matters, as you're moving faster and faster, you have to reinterrogate the scene faster and faster. You find that way of looking at the world, excuse the pun, is probably suboptimal. So what we decided to do was say that, okay, if it's going to be solid state and it's going to be intelligent, we should probably do what a human does, which is at least give the opportunity of the system to decide whether it wants to see in 2D and 3D at any point in the frame. And so what we did was mechanically fuse a camera. And in our first implementation, it's just a very standard automotive low light camera, which we sourced from one of the top providers. And what we did is took the pixels in the camera, and because we decided to fuse them originally, they are actually every voxel shot, every laser shot is 100% bore-sighted or mechanically aligned with every pixel. So from the beginning, the camera is LiDAR, the LiDAR is camera. And now all you have to decide is that, do you want to take the 3D data or the 2D data? We call this concept a new data type called dynamic VXLs. We call it VXLs because, again, we're so creative. We have a great name, which is you take a pixel and a voxel, you put it together. Now, there are VXL lasers, which some people on the podcast who are very technical competent would say, this is not a VXL laser. This is just taking a pixel and a voxel and fusing them. The reason we call it dynamic is because the wavelength we use, 1550, is an amplifiable fiber optic laser, right? So in essence, I can not only decide whether I want to see in 2D or 3D, but I can also change the power at any given point and any given shot. And that makes it dynamic. So if I happen to want to see further at a certain part of the scene like a human does, I will foveate and put more power on those dynamic VXLs in the middle of the scene. If it happens to be raining or snowing and I need to cut through on the horizon, I may want to shoot more power at the horizon so that I can see further or I can see through obscurance. So in essence, creating this data type just allows you to do what a human does. But because we are using a computer behind the scenes, we can actually do it better than a human does, right? Because we can do it faster, up to 100 hertz, and we can do it further, up to 1 kilometer, using that dynamic VXL concept. So that's the first step. The first step is you made a decision it's solid state. The second step is you made a decision that 2D and 3D need to be fused at the point you acquire information. And then the only other thing left, really, is the fact that you need to be able to decide if you see something like a human does, could you actually change the pattern to actually gain more information? right? And we'll call that the ability to be agile. So, for instance, if I see something out there and I'm scanning the whole scene at the same, what we'll call search pattern, which is what we do in the military, I'm searching. If I happen to see something I'm interested in, do I have the capability, while I'm still continuing to search to see if things are in the scene, do I have the capability to acquire a target, right, to put more focus on that target? So now that I can see in 2D and 3D and I can change the power, and my Lidar system is not on a fixed pattern, it can decide to shoot anywhere it wants. If a camera happens to see some contrast and some edges, which it's extremely good at, we laugh at the argument whether computer vision is better than 2D computer vision is better than 3D Lidar. They're both better in some circumstances, and they can both help each other. To us, 1 + 1 = 10, right, when you get to decide how to use it. So we can then acquire a target either using the camera or the Lidar system and changing the way we actually interrogate that target while we're searching, and then we can decide what to do with it. So that's the way that most automated targeting systems work in the military. Always search the scene. All targets aren't equal. Speed matters when you're acquiring a target to decide whether it's friendly or unfriendly. So we're just trying to take some of the technology concepts that have been around for a while in the space program, in the military and intelligence, and we're trying to apply them to helping not hit people versus identifying objects that may be threats overtly to you.
Right. And so you talk about this fusion of kind of the camera and the Lidar as being a physical thing. I'm having a little bit of trouble in my head imagining kind of how that works. But they operate together, and then you're saying that whether you want to focus 2D or 3D in any particular moment, that happens by shifting the amount of power to one or the other?
Well, you can decide to interrogate the data. The camera that gets 2D is what we'll call a passive sensor, right? It's always going to collect data on all the pixels. So the Lidar system we'll call an active sensor. We're searching the scene in different patterns in different ways. And at any given time, I can decide, do I want the Lidar data, the 3D data, or do I want the 2D data, the RGB data, or do I want the RGB data and the depth data? So let me give you an example of each of those and why in a different situation you'd want one or the other. So for instance, in a situation where it's a very sunny day and the camera's doing a great job of interrogating, you could actually see an object, you could see the contrast, and you could actually identify and use a shallow learning stack to tell me that's an object and it's moving, not moving, and it looks like it's, a human, right? Those situations exist, and that's when a human would use that methodology, or and it makes a lot of sense. The camera leads the way. There's other situations where I enter a dark tunnel, or I'm in a situation where there's shadows, where I may actually want to use the Lidar system first to identify that there is an object and that it's in the road, and that while the camera's not verifying that, I want to three-dimensionalize that, and I want to put some effort against it because the camera may not see it, but the Lidar does. And when the camera can verify it, it will actually come back and add to it. The most important situations are the ones where we actually combine both. So for instance, you're pulling up to an intersection and you see red. Okay, the camera sees red, but it doesn't know whether it's a tail light or it's a stoplight. They would have to run a computer program around that to try to verify that in some deep learning stack. If you have a Lidar system, I can tell the distance, the depth. I can tell whether it's a picture of a stoplight or a real stoplight. I can tell whether it's a tail light or a stoplight, because now I'm using 2D and 3D at the exact same moment, like a human does, to decide what it is and how I want to react to it. So we call that situational analysis, situational awareness. The system itself will either use the camera, the Lidar, or both to actually verify what an object is. And once it decides, it can then change how it deals with the object that's in front of it. So while this sounds fairly sophisticated, it's truly biomimicry. We're just replicating with multiple sensors how the human brain would actually interrogate an environment.
So it seems like there's also then this embedded AI in your product. And so, you mentioned earlier kind of moving the processing earlier. Can you explain kind of how that piece then works with these 2D and 3D sensors that you have?
Sure. So the easiest way to think about this is that the first thing when we talked about our 4 things we wanted to replicate, one of them was processing on the edge, right? Which means that the sensor itself can start to bring back more than just data. Part of the challenge with building, multiple sensors that collect everything that they see and they bring them back to the hub is this challenge between density and latency. If you replicated what we do today in a lot of autonomous vehicles, which is bring back all the data about everything, including everything about the sky, everything about the trees. Some systems like to show you that they can see the lines on the leaves. If you bring it all back to the center and you try to process that, that replicates in a lot of cases what we would attribute to human autism, right? A lot of information coming down, and you've got to apply a lot of power and a lot of focus to decide what matters and what doesn't. Maybe not the dirty secret, but the reality of the situation is that most systems that bring in 2D and 3D data in autonomous cars today, not only does it take them a long time to fuse them together, between 70 and 90% of the data is ultimately thrown out because it doesn't have anything to do with what you're trying to do when you're driving. So the ability to have what we'll call shallow AI, that the camera can talk to the Lidar system because they're one system, because they're mechanically fused together, so that they see exactly the same thing at the same time, allows you to very quickly modulate between the 2D and 3D. We call that shallow AI. Now, there's 2 other loops that never existed before in our system that exist in say, other more sophisticated systems in different industries, right? So one of those is that if I bring back information to the perception system may tell me, I would like to I know I'm using an HD map, and I know there's a trigger on the map that tells me that there's going to be an intersection coming up. And I know if I was a human and I had been driving a while, I would know that my threats come from an intersection when someone runs a red light from a lateral movement. And I would actually put more density as I approach the intersection into the pieces of the intersection that have entry points. So I would repurpose some power, and I would watch those very quickly. Or for instance, a more abstract example of this is that one I just did with my son the other day, we were driving down the road, the trunk was open on the car, there were no people around the car, and I said, hey, you know what, you need to drive defensively, go over to the next lane. And because I knew, and exactly what happened, that there were people that were going to load the trunk, and there was a small child that came around the side of the car very quickly carrying a bag of groceries. Now, again, those are 2 examples. One is a proactive example. I know from experience that I can put high density on the intersections. I'm going to look left and right and make sure there's nothing coming. The second is a probabilistic prediction, which is when I see one thing happening that I'm going to predict that I want to actually take some action beforehand. So that's a different type of AI. And again, it's not a deep learning stack. I still didn't identify the object. In either of those cases, I identified a blob and I identified that danger could come in. Now, there's the third type of AI, which is that I know I'm going to turn right. So if I'm a human, if I know I'm going to turn right, I actually foveate to the right. Our system can take a feed from the system and say, I'm going to foveate right. I want to make sure that while you're searching everywhere, you also put some long distance to the right because you're going to be turning right. Today, none of the vision systems, the cameras or the Lidar systems, can use any of those feedback loops because they're basically simple sensing or passive sensing. So all the systems that we're using on cars today are search sensing systems. They're just passively sensing, and they will send you back a signal when they see something. They have no capability to actually search for something and acquire it or predict that something's going to happen. Now, I can tell you, if I talk to different people in our industry, there's no one in the world that will argue with me. That's not where we want to go. I think the bigger argument is in autonomous cars, and we have one side of this, and there are people out there that have another side of it. Our prediction, given that we've seen this in other industries before, is that it's better to intelligently search than it is to passively search. which means it's a system problem, not a point sensor problem. And while we want our sensors to be more powerful and faster and cheaper, we will actually, if someone else can build one, we'll actually use their sensor in different areas to get that data. But for us, it's really about the information content that goes back to the perception software and the path planning software. So we're really a toolkit that helps software companies actually manage information, not data.
So when you talk about the products that mostly exist today where, 75% or more of the data ultimately is discarded because it's redundant or not helpful, how does your system know what the data is that matters and make sure that you're not discarding data that might have actually been relevant?
No, and that's the number one question we get at the beginning of every meeting, is that, well, if I don't collect all the data in the world and throw out 90% of it, how will I know I didn't miss anything, right? And so this is usually where we start. Well, if you did that, you couldn't function when you got out of bed. So how do you do it? And then we take them through the process. We can collect all the information that we want. So let's take the first step, which is I'm going to actually take the exact same way you collect all the data today, but because my system is intelligent and it's built on a different type of solid state Lidar, I can do it with less power. So I'll give you what you have today, and then I'll add in on top of that the ability to do deeper searches within collecting all the data. And the question for you is, do you transport all the data back, or because you can do these deeper searches, do you only transport back the data at the edge that you verified that there really is something there? Because when you really look at the mechanics of it, collecting that data and keeping it organized and tagging it and bringing it back, there's 10 times more power bringing back something and analyzing what's in the scene at the core than there is at the sensor level. So our first answer is, I'll give you all the data, but why don't you do your processing at the edge, right? The second answer to that question is, tell you what, why don't we do a really easy screen? If I can prove you that we're looking at the sky and I know it's the sky, can I do a randomized pattern in the sky instead of trying to get everything? That's just as effective to see a bird coming at you, but there's very little in the sky that matters. And given that you're looking at the road in front of you, both 5 feet in front of you and 100 meters in front of you, how about I tell you that while I'm collecting the data 5 feet in front of you, when I see that I'm using too much power, which means it's bouncing off and wasting power, I'll modulate back the power to collect it optimally at 5 feet, and I'll use that extra power to collect it at 200 meters in front of you. They say, okay, all you're doing is actually allowing me to more effectively get rid of, do I need the leaves on the trees? The answer is no. So if you have a GIS system and you want to collect everything in the world and you're willing to process it overnight and use a lot of power, you can do some intelligent big data analysis. The problem is you're trading off density and latency. So either allow me to process it at the edge like a human does, or allow me to eliminate objects that I know are not useful to me. I don't need the leaves on the trees. I don't need to use 200-meter power on road 5 feet in front of me. And so what we do is we slowly but surely help the system architects decide how they want to interrogate. So our job is not necessarily to tell them what the objects are. That's the perception system's goal. Our goal is to help perception systems collect data more effectively, more efficiently in 360 degrees. So it's a subtle difference, but it's a very powerful difference. It's the difference between being a visual cortex and the difference between being, a brain and actually processing all of the information into actions.
So how then does the embedded AI in your products interface then with other software along the AV stack?
Right. So it's a great question, right? So now that you've said, okay, you guys are a toolkit and I can decide how to collect data, we also give you alternatives. One alternative is you've already built an algorithm that sits in the trunk, on a computer that analyzes to look for things. I will allow you as a platform to drop that algorithm right into the sensor and just do it on the edge, as I said. Now, that's your option, and we've tried that. In fact, we showed that at CES, where we took a pedestrian tracking program that was used as in the core in a trunk to take Lidar and camera data and to actually track pedestrians. We just dumped that directly into our IDAR sensor, and they were able to run it at high efficiency on the very edge of the network. The second thing we tell you is that you tell us what kind of data you want, and then we'll tell you how fast we can get it to you and what density. And that's another way that people can use our system. Again, we're not trying to tell you how you have to interrogate the environment. We're giving you options. And then as you run simulations on it, you'll decide what options. What we have found is that my argument back to the question, because this is always the question our competitors give us, well, if we don't collect all the data, they're going to miss something, right? So the answer back to that is that philosophy is that I actually cannot interrogate intelligently my environment in a way that actually adds more information content so that I can make better decisions. And, one example of someone who did that extremely well is Mobileye. Mobileye's market dominance really had a lot to do with the fact that they basically took a camera and they built a chip behind the camera, and it was brilliant, and they pre-processed the information, so they weren't actually bringing back tons of information. They were processing data into information and then transporting it back. If you think about our architecture, it's an example of using, again, we try to learn from everybody. It's an example of using that type of intelligence, but doing it on a system-wide basis where we make some assumptions that 2D and 3D do matter and that edge processing does matter. So what we believe is that we're a toolkit, and we're a toolkit for visualization. And again, our goal is to allow you to collect information better than a human.
So what types of companies then are you selling your products to? Is it OEMs, tier ones? Like how does your product get integrated into this whole? And then we'll talk about kind of ADAS versus a fully autonomous vehicle. But in general, how is your product being sold?
Yeah, and you're very well versed on the marketplace, so you actually brought up something that most people wouldn't. There is a big difference today between mobility and ADAS and how you go to market. And therefore, there is a slightly different emphasis on who you have to talk to and how you have to talk to them. So if you look at the mobility market, which in some respects people would say, now there's cases where, there has been computer vision systems doing ADAS, and there's been a couple of low-end LiDAR systems doing ADAS. But if you really looked at the major investment in the market for mobility in the last 3 or 4 years, you can see that a lot of people have gone directly to the OEMs, and the OEMs have built large organizations to do testing. But now what you'll see 3 or 4 years into it is that the OEMs are also working with their preferred tier ones in a lot of cases, and they're focused on more of the higher level abstractions. The ADAS market, which I would say has really picked up in the last year to 2 years, that has been out of the box. The OEMs have been on the front of it, but they've also embraced the fact that they would like you to move with tier ones, because it's integrated product, it's high volume product, and it's lower cost product. So I'd say how we're interacting with people is dependent on whether they're looking for a mobility or they're looking for an ADAS solution. I think 2 or 3 years from now, the line between those two are not going to be as clear, because I do think that ADAS systems make a car smarter, and so that it does some things autonomously. I say the difference today is that an ADAS product is a consumer product that adds value to a vehicle that they buy, and that mobility products today are predominantly focused on a B2B sale to a service provider who can find a way to monetize the ability to lower the cost of logistics, right? So if you sell to a customer and you're doing mobility, it's got more to do with how you lower your costs and get to a customer. When you're an ADAS product, it has more to do with how an OEM can add more value and therefore charge more for the car.
Right. So is your technology deployed in any vehicles that are on the road today or just in vehicles that are being tested?
Yeah, so if you look at vision systems today, so we are, we have a list of strategics who invested in us, and all the strategics who invested in us are using us in one way or another, and we're also involved in pilots with a variety of people in mobility and in ADAS. I'd say that what makes us slightly unique is because the architecture we built was a scalable architecture, again, that we can plug and play. We are, arguably, and I'll say arguably because there may be a competitor that can make an argument the other way, is that we actually play in mobility and in ADAS. Most people are focused on one market or the other, because when you build a fully complete product, it's usually designed mechanically as a physical product for one market. Since all of our products are software definable and built on an architecture where you can slip in and out, we can actually build a very low-cost product with what I would say constrained performance for the ADAS market, and we can actually scale that same architecture up and use different lasers and different receivers, and we can actually do a more comprehensive product for the mobility market. So today, I would say, while there is maybe, and this is, for your listeners, there could be 70 LiDAR only companies, and there could be 120 computer vision companies out there, and there is absolutely 50 to 60 radar companies out there looking at what I would call component companies. There's probably only 3 to 4 companies in mobility that have a system that ranges from passive systems to maybe our active system, and there's probably only 4 to 7 companies in the ADAS market that really have a system architecture, that they have a product that's far enough along. So while it does seem like a very crowded market, there are definitely a lot of people looking at innovation on the component level. But for companies that can actually produce a product and actually get into a car, there's very few. And so I think that you'll see in the next 2 years, the auto industry is very smart, and they are maturing very, very quickly, and they're moving very quickly into this. They want architectures that they can adapt and that are system optimal. So I think we're in a big change.
So, I think most people don't think of having a LiDAR component in an ADAS product. Do you have customers that are thinking about putting your IDAR product in a level 2 ADAS, or is there someone building a level 3 ADAS vehicle that plans to use IDAR?
So I can tell you that from what I've seen, that there is not a major car company today that does not have a LiDAR RFI, or majority of them moving to RFQ, right? And there's a reason for that. So when you talk about level 2, what you mean in level 2 is it's the intelligence means speed, consistency, and resolution. So if I'm going to do an automated braking system, or I'm going to do some type of system that is functioning, that has a very clear binary yes or no, if you can get the LiDAR system to be at the right cost, then you'll compete against cameras and radar systems, and there are definitely RFIs and RFQs for that. The further up the stack you go, where you have to add more intelligence into the system, and you need 3D with RGB, then LiDAR systems are absolutely the only way to get there, to the 3+. There have been in the past, Audi had tried a LiDAR system in its A8 as an option, but I would tell you that I have not seen an ADAS RFQ recently, or an RFI recently, that hasn't looked at adding LiDAR into computer vision. And I've not mentioned radar at all. I respect radar tremendously. In fact, half our company has a radar background, but we look at radar as a trigger sense, the same way humans look at the ability to sense something different. So 2D and 3D is the way I interrogate the environment. Radar may tell me that there's something out there that I need to go interrogate. It can see longer. It can see through weather. It's fairly inexpensive. I mean, radar is not going away anytime soon, but again, it will be how you decide to impact that into a system. And our architecture, radar, we're a redundancy to radar because we can get velocity and we can get velocity and vector laterally. So we can actually be a redundant system to radar, but we can also work with radar as radar sees something and we may say, let's go figure out what that is. So that's kind of the way the market is today. I think that, again, the good news is that there's a lot of investment going into all of these component technologies, and I think you're going to see huge jumps. I mean, we actually look at how we can increase our or put new components into our architecture every 3 months.
So when you look at your product being a combination of Lidar and camera, and you see that as a important component both for ADAS systems, let's say level 3 and below, and for fully autonomous vehicle systems, level 4, and you just view that as a continuum, but assuming the cost works for folks, you anticipate your system really being applicable in any level of vehicle, not just a level 4.
That's the way we market today, but in the sense of full disclosure, is that we market the lower end products through tier ones because we think that, and it's not only lower end in the sense of less valuable, but when you're working at a level 2 ADAS system, we would rather license out our technology to be integrated by someone who can do it more efficiently in volume. Whereas in mobility, we work with tier ones, but we work more as a partner. So for us, the only difference is how you implement. It's not necessarily whether it's a right or wrong. It's can I get the cost down and the reliability, up to the point where I can make the customer happy with what they're looking for.
Right. And when you talk about mobility, you're talking about companies that are providing a fully autonomous ride service.
Right, and I would say that's it's a B2B sale for someone who's going to build a service on top of this functionality. Now, there's something in between ADAS and what you'll call robotaxi, and that's the mobility and demand markets, right? Which have some attributes of ADAS in the sense that the functions. It's not every function that you need because you're on a constrained route, and you know where the obstacles are, and you also have defined in a mobility and demand, a bus that only goes around one campus or a shuttle that allows you to take students places. It's a more constrained environment than pure mobility or robotaxi. So it uses some of the contributions from ADAS thinking, and it also needs some of the things that are being developed in the robotaxi market. So, for instance, the ability to see longer distances and the ability to see objects entering laterally. Like when you talk about edge cases, I mean, one of mobility's biggest or robotaxi's biggest edge cases is this lateral entry of objects because radar can't get velocity coming in from the side, right? And so Lidar like ours, the way we do it, we can do that, and it just adds, to the solution. So you'll use that in robotaxis, but you'll also need that in mobility and demand. But there's other things that you will not need that you need for robotaxi in mobility and demand, making it a more constrained and a more straightforward solution. So, think of it as a spectrum, right? And at the end of the day, if anyone tells you that computer vision is the best in the world, or Lidar is the best in the world, or radar, or the way we're configuring it without telling you what they're putting it into, what the use case is, then they're really more of a technologist. They're not talking about customer productization, because it really does depend. At the end of the day, the customer is the person who defines, how they're going to constrain the use of the technology.
Right. So you mentioned cost earlier, and I think for most of us who have been looking at the autonomous space, we've always heard that the cost of the Lidar is this huge problem, as well as, speed and some of the other things that you're trying to solve for. How much does your product cost compared to kind of the original big spinning Lidar that was first available? And, how much more do you think cost needs to come down for this to be part of all ADAS systems in cars that get sold here?
Yeah, listen, that's the probably the most important question for implementation is at the end of the day, size, weight, and power, not, and cost, right? Swap C. So the LiDAR-only systems have been really working on that. In our system, yes, we're integrating a camera and some AI and a chip, but in reality, a LiDAR system is a big part of that cost structure. So what I can tell you today is that what we believe in the next, 2 years at volume, systems started out at, you need $150,000 per car, and now you're down to $80,000 per car. People are talking about bringing that cost down for LiDAR-only systems. Our belief is in order to really implement robo-taxis, you need to get under $25,000 to get 360 degrees with all the intelligence you need to do a level 4 and level 5. We think that's, and the reason we believe that is if you do the mathematics, the average car is used 4% of the time, and then you add in all the costs, maintenance costs for garages and valet parking and things like that, and you do the math on it. If you can use a car 90% of the time and you can bring the cost down below $1.50 per mile, it is a completely different market. And that's where the service providers make money. They can do a lot of different things with a car when the cost is that low. So we think that we're not there yet in either LiDAR. But our philosophy is that, per sensor, on a sensor per sensor basis, you're going to have to be below $2,500 for robo-taxis, and you're going to have to be less than 3 or 4 sensors per car in the long run. But today, I think, $25,000 for cameras and LiDAR and some software on the top of a car, you can make money as a B2B. I think the ADAS market is going to be a much tougher market for people, because if you take a look at, say, what, lessons learned, I mean, I'm a historian at heart. You go back and you look at what good people have done, and you look at patterns, and then you look at where you can disrupt those patterns. You're going to be competing on the low end against camera systems that are very inexpensive and that you can put more and more camera systems on. And there's people trying to figure out, like Elon Musk would argue, if I push hard enough on a low-end system, someone's going to figure out a way that I can make it work, right? Or a radar system. So ultimately, you're going to have the new LiDAR type systems still be under $500 to compete with those systems. So there's a big difference between, say, a mobility system where you have, 3, 4, 5 sensors and they're $2,500 a piece, and an ADAS system which you may have 2 sensors and they're going to be under $500 a piece at cost at volume over time. I look at our job is to find a way to meet the use case of the expert, which is the OEM and the tier 1, but to do it at a cost where they can make enough money that they can pay me. Or opposite, they can, I can make enough money that I can actually be a good vendor to them. And we just think that the modular approach that we've kind of taken, where you can continue to plug and play, we look at this and say, look, to one of these systems, there's not that many components, right? There's receiver, there's a laser, there's electronic boards, and there's chips. And all of those components, over time, there's great people pushing the cost down. You just have to be agile enough to be able to take that in. One of the things that I struggle with, but again, I respect a lot of people have built factories early in this cycle to build LiDAR systems. And I just don't think the market has shaken out. And I think when you build a factory, you get too wedded to your own tooling and your own designs, right? I think that, at the end of the day, we're going to see tremendous innovation, and we'd like to take advantage of that.
So your company has raised a $40 million Series B. What are your goals for 2019 and 2020? What's on the horizon?
Right. So I think this is the year of Gen 2 visualization. And I think Gen 1 was, look, spinning hardware systems. And in fact, there were a bunch of companies who have brought the cost down of spinning systems. And it was a generation of spinning systems and then separate perception software stacks. There's great work done by people like Argo and Cruise and Aurora. I think Generation 2 is going to be solid state, scalable, Lidar systems that they're going to be intelligent versus being passive collection, and that the perception systems like the Argos and the Cruises of the world are actually going to reach deeper into the hardware and have the ability to not just control or analyze what they got as a passive set of data. They're going to be able to ask for certain types of data and get it back. And so I think that's the next 2 to 3 years. And I think there will be a huge drive towards, excuse the pun, towards productization of products like that. That everybody on their roadmap, if you listen to them, is already saying they need solid state. A big portion of them are saying they need to move to an amplifiable wavelength like 1550. Another big portion of them are saying they need to add more software in so that they can integrate more with the software and adapt themselves. So I do think you're in what we'll call Gen 2 of perception. And I think that the key for us and almost for anyone else is that it's becoming a data business, and that you've got to win jobs and get on cars. Because 3 years from now, what people will judge you by is the value of the data that your perception system produces. They won't be talking about sensors and bits and bytes and speeds. We'll have all that solved. They'll be talking about the richness of the data that is produced. And so that will probably be the third generation, is that you'll start to think of this business as a data business versus a hardware or software business.
Right. Well, I guess a lot of the world is going in that direction. Everything's a data business. Well, thanks so much for taking the time to talk with us today. I really appreciate it.
Oh, well, listen, thanks for allowing us to do it. And I hope that, this is one perspective of the world. And what I found is that, there's a multitude of perspectives. And when you compare them against each other, the truth, it's time to truth. Right. So we believe that we are getting the truth fast, but we're always willing to adapt and to learn from our customers.
Terrific. Well, this has been a really interesting discussion. Thanks again for joining us.
All right. Well, thank you.
Thanks again to Blair for joining us. If you're enjoying the podcast, please leave us a review at Apple Podcasts or wherever you listen to your podcasts. You can find the show notes for this episode and all of our episodes on our Medium publication called Smarter Cars. Thanks for listening. We'll see you next time.